Okay, so some more equations with undetermined coefficients where we try a guess and hope it works out and then kind of alter the guess if it doesn't. So this is for second order equations that have a forcing function. That have a forcing function over here. That's either of the form some polynomial times cosine of omega x, so there's some frequency here, plus some other polynomial times sine omega x. They have the same frequencies. These polynomials can be different. They can be just constants, which is primarily the case we're going to look at, but I'll show you how to deal with it when they're not. And then also if you have the forcing function equal to the sinusoidal input, so some sort of wave, some sort of oscillating thing, it being amplified by an exponential force, okay? And then again, what to do if your guesses actually solve the complementary equation. You kind of just pump it up by x, essentially. But let's take a look at a few examples. Or well, first, I'll show you what you would guess, and we can pretty much see why we think it would work out, and then we'll do one or two examples. So for the first case, if this forcing function is equal to just some polynomial times cosine plus another polynomial times sine, there's no exponential piece, then what we would guess is that the forcing function, or that the particular solution is going to have the form some a of x cos omega x plus bx times sine omega x. All right, so we would guess that they're being multiplied by some other polynomials that made it through the system and ended up in this way. And we would guess, we would hope that A and B have the same degree as the max of the degree of P and degree of Q. Okay, so meaning, you know, if this is a degree 2 polynomial and this is a degree 3 polynomial, then A and B would have degree 3. Okay, because there's no way they would have made it through and been a lesser power without producing some x cubed term, if that makes sense. So they would need to be the same degree as the higher of the two. So that's what we would expect. And then there is a caveat here where this is, you know, as long as cos omega x or sine omega x isn't a solution to the homogeneous equation. Okay, which we looked at in 5.2, 5.3. All right. So if this is the forcing function, this is our guess, and then we can go through with that substitution and figure out what A and B must have been, right? Undetermined coefficients. For the second type in this section, where we have an exponential factor on this, e to the alpha x p cos omega x plus q sine omega x. Then we try the guess of, let's write it like this. Some a polynomial times e to the alpha x times cos omega x plus some b polynomial same thing applies. A and B would have hopefully the maximum degree of P or Q. Okay, and then we have another caveat, which is that if the guesses are solutions to the homogeneous equation, then similar to before, multiply by x or x squared as needed. Right? Because what's going to happen when we make that substitution, we'll lose u or u prime. So in order to not do that, we'll multiply it through by x so that derivative sticks around, right? Let's look at one or two examples to kind of illustrate how these guesses work out. Okay, so the first one we'll look at is the following. So we're going to find a particular solution. To y double prime plus 2y prime plus y equals 6 cos x plus 17x. So again, this applies. These are degree 0 polynomials, right? They're just constants, but the same thing applies. So we want to try a guess that our y particular is going to be some a times cos x plus b times sine x. And the max degree over here is 0, so we can expect that these would also be constants. Okay. So what we do is when we go through and try, what must y p prime and y p double prime be, and you can fly through these derivatives pretty quickly. So negative a sine x plus b cos x, and then y double prime negative a cos x minus b sine x. Okay, so then we'll throw this back into the original DE, each of these, and figure out what A and B must have been, what these undetermined coefficients must have been. So y double prime plus 2y prime plus y saying we hope this equals 6 cos x plus 17 sine x. So from here, we'll collect the coefficients of cosine. So what do we have? Negative a plus 2b plus a. So what does that mean? Do the a's drop off? Yes. So the a's drop off, and so we're just left with 2b cosine. And then we've got, for sine, a negative b. We've got negative 2a and a plus b. So the b's cancel out. We're left with a negative 2a. And this all equals 6 cos x plus 17 sine x. This one actually worked out pretty nicely because what do we see here? All right, so we'll get that this must mean that 2b has to equal 6 and that negative 2a has to equal 17. At worst case, you'd get a system of equations where you have to just find what a and b are. Here it worked out pretty nicely. So it turns out that b equals 3 works out, and a equals negative 17 over 2. Okay. So then, our y sub p, our y particular, negative 17 halves cos x plus 3 sine x for this equation. So this is how this works in general. When these are degree 0 polynomials here, when they're degree 1 or higher, then instead of trying something like this, you would try, I'll just write out an example. So just the outline of it. If we had this instead, 3 plus 2x cos x plus 3 minus 4x sine x. We'd try to match the degree of the polynomials on the right. We try y particular to be some a plus bx cos x plus some cx plus d, or we could write this in the same convention here, c plus dx sine x. Find out what yp prime must be, yp double prime. And then really it's all just algebra from here. It's nothing too crazy. You just have to find out what each of these coefficients must have been to result here. Okay, and if, let's say I had a squared over here, then what we would need to try here are a plus bx plus cx squared, and you know, dx plus ex squared plus, oh, this would mean to be just e, right, some constant plus fx plus gx squared, to go in and find what these must be after shaking out these derivatives. Okay, these are a little bit more involved than we're going to do. We're going to stick with degree 0, but just to let you know what you can expect with problems like this. So it just kind of scales up the amount of algebra you got to do in determining those coefficients. All right, so for this next example, instead of having just sinusoidal input on the right, we're going to have it being scaled by e to the x. Okay, so now it's got an e to the x times this sinusoidal input. So what we know is that we're going to try a guess of y to the p, which is going to be, you know, ax e alpha x cos x plus b of x e to the alpha x sine omega x. Here our omegas are 1, our alpha is 1, so should simplify the structure of it pretty well. There's one other thing I was going to say here. Oh, to use the same method we've been going about. So let's not, this is what your guess will end up looking like. This is what your y particular will look like, but we still want to try the method of, u e to the x. So if my forcing function, the solution to the system here, is a product of e times something, we're going to try this out as our y particular, some unknown function times e to the x. And then we'll end up deriving this along the way. So if that's the case, like we've seen before, this yp prime would be u prime ex plus u e to the x. And y double prime is u double prime e to the x plus 2u prime e to the x plus u e to the x. Right? So therefore, if we plug this into our initial system, get y double prime plus u e to the x plus 2y prime plus y. And this equals e to the x, 6 cos x plus 17 sine x. And what this allows us to do, obviously, is kind of snap off the e to the x and be left with u double prime plus we've got 4u prime plus 4u, right? 1, 2, and 1. And this equals 6 cos x plus 17 sine x. So one thing I didn't really talk about yet is to first verify that here and here aren't solutions of the complementary homogeneous solution. So you should always take a look at the characteristic polynomial. Here we see this one is r plus 1 squared. So we're expecting, e to the minus x and x e to the minus x as being the fundamental set of solutions to the homogeneous equation. So the fact that we don't see those over here is good. That means we can proceed normally. If one of these was one of these fundamental solutions, that means we're going to need to multiply our guess by x in order to preserve it. All right. So, and the same thing happens here. We have to make sure that this is not a solution to the fundamental or to the complementary equation. So over here, we know our p of r is r plus 2 squared, right? And so this tells us that e to the minus 2x, x e to the minus 2x our solutions. And since we don't see that it's not complex conjugate roots, then we're good to go. Good to continue. Okay, so this might arise in your practice problems. So back to here. Now we're guessing, right, that u sub p, just like in our first problem, is going to be of the form a cos x plus b sine x. So this means up prime would look like this. Double prime like this. Then plugging back into our original, not original, but this equation here. Negative a cos minus b sine plus 4u prime. Let's just do that out here. So 4u prime negative 4a sine x plus 4b cos x plus 4u, 4a cos x plus 4b sine x. Getting a little crooked here. We're when this is equal to 6 cos x plus 17 sine x. So gather up all the cos x coefficients. What we get is what? Negative a, let's just do this here. Negative a plus 4b plus 4a. So we'll get 3a plus 4b plus sine x. I should maybe be writing these in front of this because you don't want this to be, this is not the input, this is the coefficient. And then for sine, we've got what? Negative b plus 4a plus 4b. So that's 3b minus 4a. Yes. And we want all this to equal 6 cos x plus 17 sine x. So from here, you got a system of equations. 3a plus 4b must equal 6. 3b minus 4a must equal 17 for the coefficients to work out. This ends up where we've got b equal to 3 and a equal to negative 2. So therefore our u sub p is negative 2 cos x plus 3 sine x. Therefore our y sub p, which is up e to the x, is just e to the x times this piece. And so this lines up with what we expected we would see from case 2. That it's some a and b coefficients here times that exponential piece with our cos and sine. Again, all that really changes with this omega is that you have to deal with the chain rule. And that all that changes with a and b being a higher degree means you just need to make them a linear piece or a quadratic piece, probably at the worst. And that if what you see on the right-hand side, if a piece of the forcing function solves the homogeneous equation over here, then you need to multiply that guess by x or by x squared where it's required. Okay, so that could come up in practice. So this does a good job of highlighting the major points. So look forward to your questions and seeing you in class.